Streaming. C'est OK.
Le zoom est en.
Un zoom, c'est un YouTube.
Ah, mais tu m'avais donné un lien zoom.
Je vais faire zoom. Ah. Réunion. Ah oui, démarrer. Et le zoom est OK aussi.
My pleasure to introduce to you Valerio SCARANI, who's a long-time collaborator, did your PhD in Switzerland, and did a postdoc there as well in Geneva, and then moved to the starting Center for Quantum Technologies at its beginning, I think, right? You were there, and I was visiting us, looking for a year, and you'll talk about the quantum wheel approach.
Thank you. It's a pleasure to be here. So here we hold the seminar in English. We can speak in French. I would love to speak French. I speak a lot of English, some Italian, some Spanish with my boss, and don't have much time to practice my French. So. Good. So I like very much this photo because this work was done mostly with Lin, who was a PhD student, just graduated. He doesn't want to go to the US for obvious reasons, since he wants to go to Europe. So he's applying for some Marie Curie and other fellowships in this moment. And I like this photo because I don't remember if we did it on purpose or not, but you see that I'm holding a green pen, and you see how much is written in green on that board, right? This is to give credit to the guy who actually understood and computed those combinatorial formulas. I was somehow, as the boss usually does, overseen from above, right? Anyway, so, well, let's see. This work started in 2021. I visited Miguel Navasquez in Vienna, and he brought to my attention this paper by Boris Tzireson, famous mathematician who had passed away just the previous year. And this is a paper posted on the archive and never cited before we started working on it. I cited him once by himself. Okay, so let's read the abstract. How often is the coordinate of the harmonic oscillator positive? The coordinate of the harmonic oscillator, meaning the position, okay? One coordinate, but think of a position, is measured at the time chosen at random among three equiprobable instants. Now, after 1/3 of the period, or after 2/3 of the period. Okay, think of a rotated Mercedes symbol, right? In the classical case, the probabilities vary between 1/3 and 2/3, but in the quantum case, between 0.29 and 0.71, of course, the classical bounds are violated, right? So for me, this was very shocking, although I will now give you an intuitive reason of why this happens, that in the dynamics of the quantum harmonic oscillator, one quantum harmonic oscillator, non-dissipative, nothing, just a textbook thing, you can find witnesses of quantumness. Right? Other than, the fact that the levels are discrete, all these are, the dynamics of the quantum harmonic oscillator, the Heisenberg equation of motion, they are the same as the classical equation of motion, right? Is these, right? So indeed, let's see what Tzireson noticed. So this is the phase space. And for instance, if I prepare my initial state at that position, and that momentum in that state, then after 1/3 of the period, the system is there. This is classical. And after 2/3 of the period, the system is there. So I would get the probability of finding it positive in this protocol will be 1/3, right? If I sample at random the 3 possible times. Of course, if I start from there, then the probability of finding it positive is 2/3. And it's kind of obvious that the phase space is divided in 6 sectors. If you are in a sector where there's a blue dot, then the probability will be 2/3. And if you are in the sector where there's a red dot, the probability will be 1/3. Now, a classical state of an oscillator could, of course, be a mixed state. Doesn't need to be pure. And so it could be a probability distribution there And so if you have a classical system and you run that protocol, the probability of finding the positive position would be between 1/3 and 2/3. And when you see it like that, now you may know what I'm going to do now, right? Because what can happen in quantum mechanics? Well, the state will also rotate in the same way, but it could have negativities, right? The analog of probability distribution in phase space for quantum systems is the Wigner function, and the Wigner function is known to have the possibility of having negative values. Right? For those, I presume all of you have met the Wigner function. In case you have not, I have just a small reminder. So this is the Wigner function is written like that. For pure states, you can do it for mixed states, it's similar. And so if these are the standard eigenstates of the harmonic oscillator, the ground state has a positive Wigner function, like a nice Gaussian, centered in 0. So if you have a positive Wigner function, you could hold an interpretation that is that actually the quantum uncertainty is just epistemic, right? We don't know what the position and momentum are, and we are sampling from that distribution, right? And there are some, whatever reason why we cannot sample from a thinner distribution, but it's a probability distribution, so sometimes you pick it here, sometimes you pick it there, and with that distribution you get exactly the quantum prediction. However, if you already go to the first excited state, then it has a negativity in there, and so this is no longer a probability distribution. You cannot play again this game of saying I'm sampling from, right? And then the negativities keep going up and down. And you see the pattern, right? So it goes one down, one up, one down, one up, one down, one up. And okay, so that's the idea of Wigner function. Is in case someone has not seen it, notice these Wigner functions for these states are rotationally symmetric. For those on quantum optics, is the fact that you cannot measure a phase on a Fock state or whatever you want to say it, right? So anyway, that's a kind of reminder of Wigner functions. And so non-classical Wigner function, also called non-Gaussian states, I mean, certainly non-Gaussian states can have negative values. And so here is the Wigner function of the state that violates maximally the Tzireson criterion, the one that gives 0.71. Well, it's not particularly intuitive what that is, right? But I have some pseudo intuition here. So you see that what this means is that it's positive here with a yellow dot, and it's negative when it's blue. It has this symmetry now, not completely rotational symmetry, discrete symmetry of rotation by 1/3. This would be the wave function, not the square of the wave function. Of course, numerically reconstructed. We don't have it analytically. We don't know if this kind of thing here is actually discontinuity. It seems to be, in which case it would be a state of infinite energy, strictly speaking. But and if you go to the excitation representation, is a state that has components on the 0, 3, 6, 9, 12, and so on, multiple of 3 photons or energy levels, with Sussau coefficients that I've not written down. Again, we have them numerically. We don't have a fully analytical formula. So how can we guess that this kind of object violates the Tzireson criterion? Well, if you look at the positive, so that the probability of finding the particle in the positive sector will be the integral over that region. And because it's symmetric by 1/3, at whichever time you measure it, it will be the integral over that region. And now, okay, the intuition is that you put some negativity there, and you put 2 positivities, so suddenly it's more positive than it should be, classically, right? The cost, of course, of putting more negativity on the other side. This side would be more negative than it classically could be. The Wigner functions are kind of strange beasts. If you wonder why I don't put more negativity there or more positivity and so on, well, do keep in mind that the overlap between any Wigner function and, for instance, a Gaussian, a coherent state, is the probability of finding the coherent state given that state. So if my negative regions were too big, I would get negative probabilities, right? Because if I make the very big negative region, I put a coherent state there, the overlap is negative, and so I will get a negative probability. So the Wigner function, the negativities must be distributed in small blobs in such a way that you never get negative probabilities for any state that you overlap with it. And that's pretty much all that we know about how negativities can be distributed in Wigner functions. It's a completely open problem up to a couple of papers like Werner in 1980s. By the way, since I'm here, I can tell you that in the original Searson paper, he was only able to prove that quantum mechanics, so he numerically got this number, and then he was able to prove that quantum mechanics does not, there's no state that get one, but there's a gap between the two, right? So, and then in our first paper, already using a paper with Werner, you know, of course, what happens? I go around the world, I give the talks, and there's a Reinhard Werner one day is in the room. And it happened to me 3 times. So I did different topics, and Reinhard said, this reminds me of something I've done in the 1980s, and so on. And then you go and check, and then the Lemma 25 in a paper has a completely different title is exactly what you needed, right? So do give your talks in front of Reinhard Werner, it helps. And then sorry, I haven't updated the slide. In our latest paper, finally published after a lot of struggle with some journal, we have these better bounds. So yeah, it seems that 0.71 is pretty much the most that quantum mechanics can do. Now, okay, here this gap, although it's not huge, it's a sizable gap, meaning you can try other states that maybe do not violate to the maximum, but still violate, and maybe are a bit simpler to write down. So for instance, this one. This one is a combination of 0, 3, and 6 only. It still violates. It's not 0666, but it's 0687. Nice Wigner function. And then if you relinquish the symmetry and change the time of probing, you might have already thought, what if I don't probe at the same time, at the same interval of time, right? Then you get even things like this with 4 excitations. This one is not symmetric at all. When it rotates in a strange way. But yeah, it achieves a little bit of violation. I mean, just to tell you that you can play with auto states. Unfortunately, we don't have a closed criterion, so I cannot tell you something. So if someone comes and says, oh, in my lab, I can do that state, the only possibility is I write an email to Lynn and say, can you check if that state violates the criterion? Or I can try to do it myself if I were to be able to start MATLAB in my computer, which I can't for whatever reason of incapacity. Okay, so there's an operational version of this for those who like operational versions. So there is an assumption. Maybe, well, I think some of you have heard about device-independent certification. This is not device-independent, it's a single system. So there is an assumption. The assumption is that the observer we are measuring, before I call position, at these 3 times or these 3 angles is related in that particular way to, so it looks like something that rotates, at least at those 3 times. So there is an observable A0 and observable A pi over 2, and then the A at this angle theta is composed in that way. So there is this kind of idea of rotation or quadrature, you would call in quantum optics. And then okay, the protocol is like that. At every round, you choose one of the values of k and measure the corresponding k projectively. And then if you find a positive value, you get score 1. If you get a negative value, score 0. And then for technical reason, I don't want to bother. If you get exactly 0, if it were possible to get exactly 0 for the particular observable, then you get score 1/2. So your total score is something like that. 1/3 is the probability of choosing one of the 3 times. 1 point if you get larger than 0, 1/2 point if you get equal to 0, 0 point if you get smaller than 0. And you can have 2 versions of these. One is the one that Searson invented and I presented to you, is that this theta is actually uniform precession dynamics, like the harmonic oscillator. And so you have to measure the observer at different times. Of course, once you are there and you remember the times makes decoherence, you can also think, well, no, I make this assumption of the observer being like that, and then I measure all of them at time t = 0. I need to measure 3 different quadratures, right? Which again, in quantum optics is very natural. Maybe in classical, in harmonic oscillator, it's not entirely clear what it means to measure cos theta x plus sin theta p, right? In space, well, what I'm measuring there. Probably to measure that, you would have to measure position at another time, precisely, to weigh these. But anyway, these are the 2 possible things. Okay, well, important thing that I like a lot is that this criterion, as you see, does not require sequential measurement. So we're not measuring the observable at this time and later that time after the state has been collapsed and whatever. We don't need any assumption of commuting measurement. In fact, they do not commute. There's no assumption of memory. So in a sense, it's more robust in terms of assumptions that things like Leggett-Gary, that's completely unrobust, and Cohen-Specker or contextuality criteria do require you to measure two observables, or at least to be sure that, I mean, Leggett-Gary requires you to measure consequentially, and Cohen-Specker does require you to say that some sort of commute, right, in a more or less, yeah. Okay, and some of you like polytopes, right? So that's when we put up our first paper. Second, then the people in Siegen noticed that what we have done is essentially, you know, if you have this thing that rotates like that, what we're doing is that we're saying that the probability of finding the particle 3 times positive is not going to happen. So in a simplex of 3 bits, this would be a cube, right? And now you say, okay, but the 111 point doesn't happen, and the 000 point also doesn't happen. And so you cut them, and you get this facet. The 111 would be here, right? Would be somewhere here, out. And then you cut this thing. And so what it says is that quantum mechanics violates this facet, right? It comes out above this facet. Okay, so yeah, sorry, I didn't know.
But, I mean, the quantum mechanics is inside the classical mechanics.
No, don't
Outside. Outside.
You can do more. You can do more with quantum than classical, yes. Okay, so this I told you what more or less what Silverstone did and so on, and now I'm going to just show you some variations. And the first variation I thought of, this actually I thought when I was quarantined because we were doing a trip with my students in the end of 2021, and then at the time of taking the plane, one of the 3 decided to test positive for COVID. And so instead of taking the plane, we were all sent in the mountains of Trento for 1 week in a beautiful place where we couldn't move out, right? And so there we started thinking of precession in real space. So this is the phase space of the harmonic oscillator. Now let me replace momentum with y, the other spatial coordinate. Can I get a similar criterion with an observable that does not rotate in phase space, so one-dimensional harmonic oscillator, but rotates in physical space? Correct. So if they commute, the answer that would be the precession. If they commute, the answer is no, because you don't have a Wigner function of x, and in x and y, for instance, you would have the square of the wave function is a positive thing, right? Psi of xy squared is the probability distribution of being in x and y is always positive, so there's no chance. But of course, you all know that there are observers that do not commute, right? Angular momentum, for instance. So here, I cannot have a Wigner function of angular momentum because the value of jx and jy are not mutually available, right? And indeed, this would be the case of fixed spin. You could try to think of this. So what does it mean to measure? So there is this vector rotating, and I'm going to make a projective measurement and ask, is it positive? Namely, am I going to project jx on one of the positive eigenvalues? And if j were to be integer, I have to get the 1/2 times the 0. If it's not integer, of course, this term is not even there, right? And so you go to, at that time, I still could go to MATLAB. I was still able to operate it. And I got a graph that looks like this, and you say, oh my goodness, the gray curve. This is the probability of violating. So you see, this is the classical one would be down here, 0.66, and that's the probabilities. You get this strange, completely hectic, although nicely pseudo-periodic thing, until recently Lin realized that this was because I'd assumed that the equal spacing of the times, if you change the spacing of the times, you get nicely these for the half integer spins and these for the integer spins. It's still a bit mysterious why it does that. We have analytical formulas for these, but at least it's a bit more flat, right? It's not this completely hectic stuff. And well, and it violates. Actually, the maximum violation, 0.75, is obtained for a spin 3/2. We have analytical proof that for spin half and spin 1/2, you can't have any violation of this thing. So yeah, j equals 3/2. That's this is in angle space. So if you choose all the angles to be the same, and then also 9/2, which is, that is a nice drawings. I shall show you that. If for 5/2, for instance, you shouldn't choose the equally spaced times, but something as a bit biased there. Well, and then you can play all kind of games, right? For instance, you can say, what if I don't divide in 3, but divide in 5 or in 7 sectors? And then again, you get this kind of stuff with beautiful pseudo-Wigner functions with the right periodicity, and there is a structure there. I will not insist on this because I have more. We have not studied later in great detail. It was in the first paper. And after that, we focus mostly on the thing with 3. Anyway, a lot of things can be done, but at some point, not everything can be done should be done, as Ratatouille says, no? Tout le monde peut cuisiner, mais pas tout le monde doit cuisiner. Je sais pas comment dire.
Just stupid. Why not 2? 2.
2 would be, each time I measure like this, the next one would be opposite, so we always cancel out. But later I have a criterion for even spacings. Okay, there are some formula. Okay, this maybe I may want to show you this. So what is the state that gives the maximum? Not too difficult to remember. Is the superposition of the maximum spin and the maximum minus spin. So let's say, for instance, here would be 7/2 plus or minus 7/2. So the two extreme. So is a spin j equals 7/2. So the values are minus 7/2, minus 5/2, minus 3/2, minus 1/2, blah, 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 7/2. You take the superposition of the two extreme ones. And well, I was going around saying, can someone do the experiment? And then everybody, oh no, yeah, I can create the state, but I cannot make the projective measurement. Or I can do the projective measurement, I cannot create the state, and so on. And finally, by chance, I chanced upon Andrea Morello in University of New South Wales, Sydney, who can do both. I mean, there is a great experimentalist in impurities in silicon, right? He controls single atom impurities in silicon and couples them for the sake of quantum computing. The Kane proposal, for those who were there in the early 2000s, right? And so Andrea has a spin 7/2, actually an antimonium nucleus is NMR, but single particle NMR, 7/2. And that's the experimental view of what I showed you in the first slide for 7/2. So again, this is the classical one, right? If you are here, you get 4, 3. So you get 4 out of 7 positive possibilities, 4 out of 7. If you do a quantum version that looks similar, like a state that is localized towards that direction of the spin, and then you move it around, you get 4 positive and 3 negative, more or less, a bit worse than the classical one, but classical one with a bit of noise. And if you create the state plus 7/2 minus 7/2, it has this fantastic symmetry, and each time you probe is up there. And so when you accumulate, if you accumulate at the right point, you sum these guys, you sum them all positive, although they're not 1. Okay, here classically it would be 1, 0. There is 0.6, 0.4, or 0.7, 0.3, but you sum all of them and you get the right result. So here is the complicated slide about the experiment. So the antimonium nucleus is somewhere there. They can actually control both the electronic and the nuclear spin, so I have a 16-dimensional object to play with. But for this experiment, we played only with the nucleus. They played only with the nucleus. And then, well, I mean, here I think all theories, so I don't need to go into the details of how they do it, but they can prepare the state, let it evolve and measure. So that's what they do there. And let me just guide you through what you have to read there. So here would be for a particular time, or a particular precession angle or time. Here you would see, okay, the probability of finding plus 1/2 is large, then there's some probability of finding minus 3/2, some probability of finding 5/2, and so on. That's the color here is the intensity of the probability of each of the 8 levels. Then, okay, you sum these numbers and you get it here. And then you take the 7 values equally spaced and you get that point. and that's the Stevenson score that goes, well, as predicted by quantum mechanics and above the classical bound. So, okay, we have an experiment. Nice. Of course, you say, well, did you believe that the experiment would give something else? No, this is the typical so what experiment, right? But like the exploration of Bell inequality. But yeah.
How close was this to the numerical or analytical bound that corresponds to this particular case?
Also, the analytical bound will be this line, and that is the experimental point.
So you're really very close to. Okay.
Well, it does require some precision because you see that between the classical and the, I mean, here the scale is 0.5, 0.7, so there's not much margin. You must be kind of precise. Your system must be kind of pure. I mean, you must really prepare the state, this state.
That it's like 10 to the power minus 3 or?
No. The precision here, I don't remember.
Okay.
I mean, we are not going for fault-tolerant quantum computing, so we're not trying to get the 0.99999, right? But okay, and now we'll go one slide by for other variations that we have done, just for you to know, and then we can discuss some of these things. So other evolutions. Well, of course, you know, when you start moving away from the harmonic oscillator, the fact that your evolution, quantum evolution, is different from the classical evolution is not maybe a great discovery, right? For instance, if you give you a potential that looks like this, you all know that there is tunneling. And so I could say, well, I mean, don't tell. There's nothing to discover that an evolution with some potential, quantum mechanical, gives a different thing than classical, right? But still, you can ask, for instance, also for the sake of experiments, you know, what happens if my evolution is not exactly harmonic, a little bit of anharmonicity, right? Or is a bit dissipative? Come on, it's always a bit dissipative, right? Does this criterion collapse immediately? And say, no, you must have a lot of purity, or it must be exactly harmonic, and so on. Well, the answer is no. And we have extended the protocol to effectively all Hamiltonians that allow for closed trajectory in phase space, one-dimensional. So continuous variables in this case. And also some dissipative evolutions. There's some related work on something called quantum backflow. This is a funny effect in which you could have a wave packet that at a given point in time, all its components of momentum are, let's say, positive. And nonetheless, for a short time, the center of mass moves towards the negative direction. After that, by interference, right? After that, it starts moving, of course, positive. It can't do much more. But there may be a short moment in time in which something where all the components of momentum are positive, still by interference of the different components, the thing moves a little bit backward. And then Miguel and others have some idea of quantum rockets. So the idea was, if I send a quantum rocket to the moon, does it arrive? Can it arrive before the classical rocket? Right? Is there a quantum advantage in sending a rocket? Probabilistic, of course. Sometimes it doesn't arrive, right? But anyway, so it's related to this kind of studies. I can tell you it's not yet. I mean, there are some advantages, but not enough to justify a startup, right? And so, well, in a paper, we studied a few things, and just for your fun, that's a state that violates the criterion for the infinite square well. You remember quantum mechanics 1, the infinite square well? The wave functions are signs that go to 0 at the boundary, and the energies go like n squared, right? Well, that thing. Of course, the trajectory is like this, right? The fellow bounces back and forth from between the two boundaries. And this is a state represented in Wigner function or in wave function that gives some violation of our criterion by the infinite square well, whatever it means. Okay, this is more important, possibly, entanglement. Okay, so you take your harmonic oscillators, and you know that coupled harmonic oscillators can be decomposed in proper modes, right? Or if you're into quantum optics, you can take two beams, send them on a beam splitter with some transmittivity, and this guy would be the equivalent of that one, that guy would be the equivalent of that one. So you're mixing the modes, or looking at other modes. And the question we ask is, if one of these two guys at the output is non-classical enough to violate the Stevenson criterion, does that mean that the initial ones were entangled without looking at the other mode? Okay, so maybe for me the quantum optic expression is more clear, but maybe for you is the mechanical one is more clear. So here I just look at this output, this is lost, and this is a strange quantum state that violates my criterion. Can I conclude from there that the initial state that I sent into beam splitter, these two were entangled? And the answer is yes. We have it analytically when the beam splitter is half 50-50, or when the two energies are the same here, so the two masses are the same. And then the rest is an SDP, so semi-definite program, so it's something that can be solved. It's numerical, but can be solved exactly. I mean, it's a rigorous certificate, so it's not like Monte Carlo heuristic optimization. And here the SDP fails in this region. So this is okay. If you see the region here, this means it's a beam splitter that doesn't have symmetric transmittivity. I mean, of course, it must fail when the beam splitter has no transmittivity, right? Because there A goes straight and B goes straight, and then there's nothing you can say, right? And here, I mean, in this model would be if the masses are the same or the frequencies are the masses are different or the frequencies are different, then these two modes are different weights, and then here you cannot certify entanglement. But for many situations here, you can certify that indeed you just look at one of the modes and it's entangled. Now, okay, well, I don't want to spend too much time. There are some interesting features of this guy, right? Yeah, I mean, most entanglement witnesses for continuous diagonal rely on a kind of uncertainty relation, like the EPR criterion, essentially x1 minus x2 and p1 plus p2 commute, and therefore you should look for that. But the uncertainty relations are always a bit tricky, right? Because you can violate them or not violate them by mistake, right? You can have more noise than expected, and so on. This one is a bit less prone to false positives. But anyway, still it's fun, whatever it is. I don't want to start a war with the other guys and so on. It's not that I'm better than the others. It is fun, right? Okay, then entanglement, n spins. Well, okay, so n spins, you have a total angular momentum, right? The total angular momentum S1 plus S2 plus S3 plus S4 plus S5 plus S6. Can you do the same thing? Of course you can, and then you write a lot of equations. At some point, that Lin and Nguyen wrote many equations. I didn't check them, but I trust them. And the result, maybe that was interesting, is that, yes, you can get a violation, and maybe this is the takeaway message. You can detect the G and Z state of K spins. Up, plus, minus, plus, no. I may say, look, okay, everybody can detect the G and Z state. But this is the first time with all the literature from anybody that entanglement detection that the G and Z state can be detected with measurement of the total angular momentum. All the other criteria require measuring some correlators, many body correlators, like Mermin inequalities or some similar things, right? This one, you really measure the total magnetization. You have to measure it, however, projectively, right? You cannot measure it on average. That's where the experiment becomes tricky. But you take your total angular momentum, you measure projectively between minus 1001 half, minus 9991 half, all the way, and you apply the criteria, check when it's positive and so on, and you can detect GZ. Almost last variation, even parity. So before I was asked, what about 2? Right? Well, with 2 it never worked, but so that's what we had there. We have 3 measurements, and we are detecting, asking whether the observer is positive or negative, right? What if I have 4 measurements? Well, this one would not work because each time, because it's an harmonic oscillator, right? Each time, if at time 0 I get positive on average, at time at the other time plus pi, I will get negative on average. So it will compensate. But what you can do is this. If you have this is what Zinyan and Jackson and Lin found, that for even number of measurements, rather you give a positive point not when it's positive, but when it's around 0, with a width of delta. So again, you have your harmonic oscillator going around, or whatever it is, or your spin, and then you give a positive point if at the time of measurement you get the spin in this region, and 0 otherwise. And again, we could have written 5 papers with all these things. We put it all in one paper because we are honest, right? We don't want to contribute to publication inflation. and the same works, including the G and Z states. So now really you can detect G and Z states either even or odd number of spins with total angular momentum. Last point, and with this I finish. I've already told too many things. With Miriam, that some of you may know, we asked the question of whether you can extend this protocol beyond quantum theory to something called generalized probabilistic theories. So something where it's a kind of more broader framework in which you have probabilities and you have some rules about observables and some form of entanglement and whatever, but you don't specify that it's really quantum mechanics. For instance, if someone has heard Gian Daniele or other people speak about this, the PR box will violate the Bell inequality at 4 and not at 2 square root of 2. That would be a kind of example of that, right? So the problem of the GPTs, the general probabilistic theories, is that they're very good at listing the possible states, but they're pretty bad at telling what dynamics are allowed. Right? For instance, if you have quantum theory, let's say for one qubit, just to simplify matters, right, is a nice sphere. So the dynamics that are allowed are such rotations, right? And we all know these. But these GPTs are like cubes. And so, well, what dynamics allow for a cube? Well, you can just rotate like that. If you rotate at 45 degrees, it goes out of the space. So you can't do that, right? It's a bit of a mess to define the dynamics in a GPT. In particular, what does it mean precession, right? We are thinking of an object where so how do you say that my generalized probabilistic theory allows for precessions? Well, after thinking a little bit, we just didn't care. We said that we requested that at the times of the measurements, this kind of structure should hold. Right? So there is an observable AX at time 0, an observable AY at time 0, and then the observable AX at time t should have that structure. Whether it's at every time t, we don't know. It's just that these 3 times when we measure them, it should look like this. Then we added a couple of universally accepted assumptions like mixtures are allowed and this kind of stuff, right? Otherwise, you get some strange effects. And then we had to fix the spectrum. So I have to say, what are the when I make a measurement, what are the possible values of these things? And the result is that for every spectrum, we can find a quantum observable at saturated bound. So this means that contrary to the Bell inequality case, where this kind of theories go up usually above the allowed quantum bound, here there's always a quantum observable that saturates the bound. So there's no advantage in going to these generalized theories for this criterion. And it looks like this. So this would be a spin 3/2 theory. So these are the allowed spectrum. And this is what you can achieve with these general probabilistic theories. And quantum mechanically, you just take the spin 3/2 and you get that thing. And then here is another, this is what we call a clock. So this is a system where the allowed states are like the 60 divisions of a clock, right? And then again, an analog clock, then you measure 3 times and you get again something similar. This is you see, it's a bit bigger. It fills the cube a bit big more than that. But okay, so that's the spectrum and you get some things. Anyway, ça prend le temps qu'il trouve, no? Okay, so I finished. This is the 3-dimensional version, a bit fishy in the colors. I don't know why Lynn decided to use this color once, but that's a 3-dimensional version of the Wigner function that violates the Searson criterion maximally. Okay, we have gone a long way on that path. And well, I would like to see more experiments, not again because I don't think that quantum mechanics is correct, but because I think that it is a kind of tough experiment to do. So once you, as an experimentalist, you can prove that you can do this experiment, you really have a very good control both on the state preparation and on the measurement. And with this, I finish. Thank you very much.
Yeah, I have like questions on almost every slide, but maybe maybe I should choose. Let's start from the end about GPTs.
Mm-hmm.
So, of course, defining dynamics and precession are terrible things. But you had a slide very early on where you said we can get rid of that and just talk about a set of observables like in Copenhagen. Let's look at 3 observables and see if what happens if we measure them simultaneously. And here you can do that. You can forget your dynamics and just say, here is a set of observables. Let's measure them simultaneously. And then probably you can get rid of these cosine and sinus things there, because the sine and cosine bring you a bit too close to the Bloch sphere, right? Or something kind of spherical or whatever. But if you just say, I have a set of 3 observables that I want to measure, then maybe you can forget these cosine things and get into real GPTs that are really far from quantum theory. And then the violation may come. Because, you see, this spherical thing is too close to quantum.
Yeah, I mean, the only thing there, you would need to make sure that the classical bound is not trivial. So that
of course.
you need to ensure that these observables satisfy a 2/3 instead of but that, yeah, I agree that that could be. I mean, all these things. I mean, as you know in research, right? These things develop
All the time.
All the time, and then suddenly you realize that thing while this paper is already submitted, and then you don't want to change too much, and then so yeah, I'm sure that there can be variations that are smarter than what we did. Yes.
So this state that maximally violates theorem inequality, can you try to use it for other applications like sensing or?
Very good. Sensing we have not tried. We were hoping to do one of these bosonic error correcting codes, and we realized that the thing does not satisfy the Neal-Laflamme criterion. So too bad. I mean, it would have been nice if this Thieleson criterion would have been a way to certify that you prepared a decently good qubit, encoded qubit, right, in that bosonic thing. But unfortunately, it doesn't seem to be a good idea to build an error correcting code on that. Yeah, after that, I have not, I don't know. I mean, okay, Lin moved on from this. So from the entanglement thing, he realized that there are ways of detecting Wigner negativity using the characteristic function instead of the Wigner function. Which is something that experimental groups, especially in ions and superconducting qubits, now they tend to measure the characteristic function. It's the Fourier transform of the Wigner function. And so, of course, once you have the full characteristic function, you Fourier transform it, you get the Wigner function. But similar ideas to these, unrelated now to the Thieleson protocol, led him to develop a criterion that you can measure like the 4 points of a characteristic function and already get a certificate about negativity for the state, right? Which is kind of convenient, or negativity or entanglement or whatever. Which again is one of these things that you say, well, you start having 4 bosonic modes in 4 superconducting cavities all together and so on. So tomography would be a kind of nightmarish stuff, right? And then with a few measurements you can. So there are some offsprings of this thing, maybe not exactly in the Thieleson sense, but more like the guy who worked on it had smart ideas. Yeah. But again, I'm very happy to, if someone finds some applications or some useful applications, I'm very happy, yes.
Can I continue? I don't know. At some point, just stop. Until you had your slide, can you go to the slide with the even number? Because until you had this slide, I was thinking, well, it's going to be working for odd numbers like Mermin tables, you know. Yes. You can have Mermin tables for odd numbers, but not really for even numbers, and so on. But this is kind of surprising. So you're saying that this form of contextuality, because I see this inequality as a specific form of contextuality that you can just pinpoint very nicely, and that's great. But you're sort of saying that if we now move to that sector, it will be for
even number of measurements. So
but not two, right? But it will be for any number of these measurements.
Starting with 4. Starting with 4.
Starting with 4.
3, 4, 5, 6.
Yeah. And does it have a sort of nice analog in terms of like now if we go back to Mermin tables, that thing we kind of saw. I was thinking about an analogy in terms of 3 Mermin 3 times 3 square and things like this. But now, does this thing have a simple analogy in terms of tables?
I didn't think about it. examples. We can discuss later or try to figure it out.
But in the sense of, from the point of view of seeing this as a witness of non-classical T, right? How would you compare it to, say, for instance, the test of the G2, right? So if you have a disputer, check,
Well,
how often do you have occurrences after the distributor? Then this also is sometimes seen as.
I mean, this thing, okay, I think that many test points, and this one will never detect anything that is non-Gaussian. So for instance, non-Gaussian entangled states, there are plenty of them, right? And like the two most we say, non-conversion, right? And then this one will never see it because it requires some negativity of the Wigner function. So that's its strength and its weakness, right? That whenever this is violated, you are sure it's non-Gaussian. But at the same time, you need to create these non-Gaussian states, right? So for many things that can be already done with Gaussian states, because they are entangled anyway, or they're Gaussian in the ensemble, yeah, this one will not work. So we tried a little bit, when we did the paper on entanglement, we tried a little bit of comparison with different criteria. So we know that this guy detects some entanglement that none of the published ones did detect. Of course, as I just told you, there are many things that we don't detect and the other guys do. Yeah, that's all I can say about that. Yes.
Any intuitions on why, when you even consider general probability theory, like that the quantum is optimal? Like, is there any intuition behind that?
No, the only thing I can say is that maybe I should have said that. I don't know if it makes sense. So, although I can fix any spectrum, for instance, this strange spectrum, and then I can find a quantum observable that somehow precesses or whatever. No, this quantum observable is never a vector unless it's this. A vector meaning that now I'm having that object precessing here, but I cannot make it precess in a different plane. You see what I mean? So usually you expect something in free space to precess to be kind of at the geometry of a vector. And if you apply the rotation that brings a rotation, it brings it out of the plane, that observable changes the structure. So the only one that remains like a vector is the angular momentum, essentially.
Can I comment on that? I'm actually doubtful that you will get, because if you look at this GPT, basically you're having a block sphere with super selection rules.
Yes.
So you kind of, you can rotate, you have complex numbers.
In that plane.
Yeah. Yeah, in that plane. Yeah, in that plane. So but my guess would be that, to answer that question, in that you get quantum that saturates because you're simulating this rotational thing. If you take a GPT that doesn't live in a sphere, on a sphere, or like if you go away from this idea that somehow you have, e to the power I angle, then you will jump beyond quantum.
Yeah, that will be possible.
But I don't know how to do it, but I think this is just because you are rotating. Then you have quantum that saturates.
Yeah. Now the point I wanted to make is that the observables that we find there are such that I wouldn't know how to. I mean, of course, you can always realize them artificially in a lab, right? But then they would not have the character of a vector that can, I could look at it different. So it rotates in that it has a pseudo rotation in that plane. Outside that plane, it would look completely different, even with different eigenvalues and so on. So if I put, so it's a little bit. I would love the guy to have a.
You don't know the full theory, right? You just say, okay, here I want.
No. But the quantum version. When I say that the quantum version saturates, I have a Hermitian observable, and that one I can really do the. I mean, I put a rotation operator and see how it transforms if I bring it outside that plane into another plane, right? And then I see that it changes the spectrum.
So what happens if your theory is real? Nothing happens. If you have a GPT, which is just a real theory.
Well, that's real.
Huh?
That's real.
Real quantum. It's all real quantum?
Yeah. That would be, yeah.
Okay, so real quantum doesn't violate. And you cannot do like spec and boxes. Because you don't know how to describe the observable.
No, yeah, I wouldn't know how to.
Seconds will not work.
Anyway, yeah, if there's some of the interest there, we can continue. Miriam is around here, right? No, I know.
Sorry?
Miriam is somewhere here, right?
Yeah, she's in our
Somewhere.
kilometer.
2 kilometers away, okay. And because it was announced by voice and not by email, she didn't know that.
All right, yeah, so there's still a lot. Thanks again.
Thank you.
Anyone wants to talk with Valerio? It's around Facebook.
Je sais qu'on s'en a un. Comment on